As we know that the conductor is a main part in solar PV system, so we are going to have the conductor sizing and how to calculate them. Actually, it's as per NEC standard, where we have to actually consider 156% of the rated short circuit current of the string to size the conductor, considering many factors like the ambient temperature, the number of conductors and conduits, and the voltage drop. So when it comes to the ambient temperature, the nominal ampacity of a conductor is determined at 30 degrees. So when the temperature deviates from 30 degrees, either up or down, then we have to consider this and use the right factor. So for example, here we see in this table for the temperature or ambient temperature between 26 and 30 that the correction factor is 1, because the nominal ampacity is determined at 30 degrees. So when the temperature is less than 30, the conductor ampacity will be higher, and when the temperature goes upward than the 30, then the conductor ampacity will be less. And these are the factors we are going to use them. Now for number of conductors and conduits, so we see when we have more than 4 number of conductors in one conduit or raceway, then we have to apply these factors, and this table is 310.15 B3 from NEC. So for example, here if we have a number of conductors between 7 and 8, then we will multiply the ampacity of that conductor by 0.7. This 70 is in percentage. And for voltage drop, it's the amount of voltage loss that occurs because of the conductor resistance. So it's like a rule of thumb that the DC side of the solar PV system is allowed to have a voltage drop less than 3%. In this example, we will have a system which has 3 strings connected in parallel and 16 modules connected in series in each string. The 3 strings are combined together in the combiner box, and then we will have single cable between the combiner box and the inverter. So the distance from the PV array up to the combiner box is 50 meters, and the distance between the combiner box and the inverter is 200 meters. And here is a snapshot of the modules, and we are going to use all of these data during our calculation for the conductor size or the conductor ampacity and also the voltage drop. So the first step that is to calculate the required ampacity. We know that our module has a short circuit, or the maximum current is 6.2, and we are going to multiply it by 1.556 and we get 9.68. This is the required ampacity. So the cable should at least carry this amount of current. So now we go to table number 3, 310.15b, and we get that we see that the cable with 14 AWG is suitable to carry 20 amp and 75 column. And also going to this table 310.15b3 to get the derating factor for more than 3 current carrying conductor and raceway, so it's 0.8. And for the ambient temperature correction, actually we account for 60 degree Celsius, and this will come 0.58. So applying these two factors, multiplying the let's say the conductor nominal ampacity by 0.8 and 0.58, which is the ambient derating factor, we get that the adjusted conductor ampacity is 9.28, which is less than the required ampacity. So in this case we need to change the conductor with a conductor that has a higher cross-sectional area. So we are going to select another one which is 12 AWG, which has the capability to carry 25 amp. Applying the same factor, we see that it can carry up to 11.6, which is more than our required ampacity, which is 9.68. So by this, we need to consider the voltage drop for the cable between the array and the combiner box. So here is the formula, that the voltage drop in percentage is equal to 2 multiplied by the maximum power current over the maximum power voltage multiplied by the conductor resistance and the length of that conductor. So from NEC there is a table 8 which gives us the resistance for all conductors. So for this specific size 12 AWG, we see that the resistance is 6.73 ohm per kilometers, and from the data sheet for the module we know that the maximum power current is 5.8 amp and the maximum power voltage is 17.5, and we know that we have 16 module connected in series, so we're going to get the maximum power voltage for the string, which is the multiplication of 16 by 17.5, and we get 280 volt. Applying all of these numbers in the above equation, we get that our voltage drop in this case is 0.0139 percentage. Now we come to sizing the other cable between the combiner box to the inverter, and we know that all the three strings are connected in parallel, so the sum of the current will be 3 multiplied by 6.2, which is 18.6, and the required conductor current is 18.6 multiplied by the factor 1.56, and we get 29.1 amp. From the previous table 310.15b in NEC, we get that AWG has the capability to carry 50 amp. So we are going to use the derating factor for the ambient temperature, which is 0.58, and since we have only one cable, then there will be no derating for the number of conductors, so it will be 1. Multiplying these two, and we get that this conductor could carry up to 29, which is less than 29.1. So we selected the next higher conductor size, which is 6 AWG, which has a 65 amp conductor capability, and after applying the same factor we get 34.8 amp. Finally we come to the voltage drop calculation, and in this case there are some factors which has been changed. The first one is the conductor resistance, since the conductor size is 6 AWG and it has from that table 1.67 ohm per kilometers, and also the length of the conductor is 200, and the amount of current for this case is 70.4, which is actually 5.8 multiplied by 3 strings gives us 17.4. So now accounting for the total voltage drop for the one between the combiner box and inverter 0.0415, and between the solar PV array and the combiner box is 0.0139, and we get the total voltage drop from the array up to the inverter is 0.055 percentage, which is an acceptable value.